This one's working now, yeah. Oh, no wonder. Hey, everyone, good evening. Thank you for coming over to our fancy office here in downtown Seattle. I know some of you have traveled a bit of ways. So this is actually the physical home of the team that builds Pravega, that is run by Shrikant over there, who's always late for meetings. And on behalf of that team, I'd like to welcome you all and thank you for taking the time to come over this evening. I do want to say that when we started the work that we're doing here at Dell on streaming, we very much wanted it to be a community effort so we could jointly raise the state of the art in this field. And I think events like this are all about that. That's why Pravega is open source and always will be, because we're very keen to work with everybody. And one of the folks that we have really enjoyed working with over the last couple of years that we've been doing this is the team in Berlin that Fabian represents, working on Apache Flink. I think from the first time we learned about the technology, we were really excited about what it can be and what it can do. You know, an implementation of a SQL-like experience for real-time analytics that people can actually use. So I think we have the perfect setup for this evening because we have Fabian first. Fabian was one of the founders of did Artisans and Apache Flink. As most of you here, if you're here, you know that. And so he's going to talk more about the Flink side of things. And then we've got Flavio, who's in the bright yellow shirt over there and also late for this session, who will come next and talk a little more about Pravega, right? And hopefully you'll get as much out of this session as I will. And please feel free to ask lots of questions because I know I'm going to do that. So if you need to get your say in, you'll have to jump in and ask quickly, okay? So with that, we get started. Yeah, Shrikant, we ready to go? Okay. Fabian, all yours. You got to use.
Yeah,
clever.
Already set up. Yeah, thanks for the nice intro. Yeah, my talk is titled Why and How to Leverage the Power and Simplicity of Apache Flink. So this is going to be like two parts. One part is like explaining a little bit like what is SQL on streams, how does Flink implement that, and then the second part is about how can you actually use this technology. All right, first a few words about myself. Yeah, my name is Fabian. I think most of the things have been said before. I'm a Flink PMC member working on Flink basically since its first day. I'm also currently trying to write a book about Flink, which is going very slowly, unfortunately. And I'm also a co-founder of Data Artisans. The company was basically founded by the original creators of Apache Flink. And we're providing the Data Artisans platform too, which is open source Apache Flink bundled with the application manager. And what this platform is basically doing, it's a bundle to productize and make productization and operating of stream processing applications very easy. And this is basically done by this stack. So we have Apache Flink in the center here there. Applications are being deployed on a Kubernetes cluster. It integrates with logging infrastructure, metrics, and continuous integration. But the most important component here is the Data Artisans application manager, which is a component which manages the life cycle of applications. So due to Flink's SafePoint feature, which allows to snapshot the state of an application, this gives a lot of power to this application manager. So you can suspend and resume applications. You can scale out, scale in applications. You can migrate applications to different clusters. And all of that is basically made very easy with this application manager component. So what is Apache Flink? For those who haven't heard about what Apache Flink is, it's basically a framework to perform stateful computations over data streams. And this also includes, from Flink's perspective, batch processing, because we consider batch data as bounded streams. So if you think of reading batch data from a disk, this also comes as a stream. So essentially, batch processing is a subset of stream processing. And it's not only Flink is not only doing like classical stream processing, it's also a framework to build event-driven applications, which is, I would say, part of stream processing, but it's not like what most people consider to be stream processing. because it goes more into this direction of microservices, building applications that that are stateful and react to outside events. Yeah, so I said before, Flink is a system for stateful computations over data streams. These streams can be real-time streams. They can be historic streams, so streams that have been recorded. The framework itself is a scalable distributed system. It's fault tolerant. It's pretty fast because most of the computations are done in memory. It supports event time processing, super large state, and it comes also with support for exactly once consistency. Flink is running in production at several large companies such as Uber, Netflix, Alibaba, ING, to name a few. And in this setup, it runs on thousands of cores, running hundreds of jobs in production. Applications have states of several terabytes. These companies also built their own internal platforms using Flink. So for instance, Uber used the SQL feature that I'm going to talk about to build an internal streaming service for their employees such that they can run SQL queries against data streams. Flink has a couple of powerful abstractions. So first of all, on the lowest level, there's the process function, which exposes control over events, state, and time. So this is a very kind of low-level interface. But this kind of interface is required to build stateful event-driven applications. So with state, you can exactly control what kind of state an application holds, how it is updated, how it is evolved, and with the control over time, you can exactly schedule when you want to perform a certain computation, how you want to relate events based on their timestamps with each other. So this abstraction on the processing function layer gives a lot of control. Above that layer is the data stream API, which provides many common operations that are used in stream processing, such as windows based on time, based on counts. Typically also map functions, filters, union, joins of streams. All these things are offered on the data stream API level, and the applications are there composed similar to traditional APIs as you know them, like from batch frameworks or And the highest level API that Flink offers is a SQL API, or also the table API, which is another representation of a relational API. And the concept here that we're using to run these queries is the concept of dynamic tables, which I'm going to talk about in this talk a little bit. So Flink's relational APIs, basically, I said it before, we have SQL. This is a very simple SQL query. And we have like link style, the language integrated style, query style table API. For those who are familiar with link, so this is like you basically don't write the query as a string in your application, but you have some kind of collection on which you then can perform certain relational operations, such as scan or group by or select, and that way you basically can compose a query. These two queries do exactly the same thing. You'll notice that the order is a bit inverted, but it more follows like the way in which a SQL query would usually be executed. Both APIs are unified APIs for batch and stream processing, which means that it doesn't matter whether the input is a static bounded input or a streaming input. The semantics of the query will be the same in both cases.
Are you taking questions in the middle or just at the end?
We can also do it in the middle.
So can I ask a question?
Yes.
What are the limitations on SQL that you support?
Oh, I'm coming to that later. If the question remains unanswered or you have a specific question for that, I can answer that later. All right, so we have these queries. How are these going to be translated? So we use a common translation stack for that based on Apache Calcite. So we see here that we have the table API on the left-hand side, the SQL query on the right-hand side. We see both are the SQL query is parsed by Apache Calcite's parser and translated into a Calcite logical plan. The same basically happens for the function calls of the table API. So both end up in the same logical plan representation. From there on, it goes into Calcite's optimizer. The logical plan is optimized depending on whether the input for the query is a bounded, a batch data set, or a data stream. And then it is translated either in Apache Flink's data stream API or in the dataset API, and then it's going to be executed. So here on the blue path on the left-hand side, this is basically the path for bounded data, and the right path is the path for the unbounded data. But again, the important thing here is that the semantic of what the query computes is the same in both cases. So what happens if we have now this simple query here, where we basically compute a simple group by query and count per user? What happens if this clicks input table as a file? Well, in that case, we can read this file completely. We get some kind of table representation here. We give it into our query, and we get a result. And the input data is read at once, and the result is also produced at once. What happens if clicks is a stream? So we cannot read the stream completely because it's unbounded. So what happens is that we are reading the stream record by record. So we have one record, and we update the result as we get more data. So you notice that here we have this first count, Mary 1. And once we get the second record for Mary, the count is updated to 2. So the input data is continuously read, and we also update the result continuously. Yes?
How frequently those data being updated? Have 1 second, or every record you will change it up?
Right now in the implementation, it updates with every record, but we're planning to change that and make that basically configurable to, exactly batch more data together and make that more efficient. But right now, we start with an implementation that gives the best latency. So, and from there on, we're gonna make it provide option to make that more coarse-grained. But the important observation here is that the result is the same. So why is it important to have this unification of stream and batch? So first of all, it's a big usability issue. So you don't have to. You just can learn the SQL that you learned at school. So you don't need to learn a custom syntax. You also don't need to learn custom semantics. So it's the semantics of batch SQL being applied on a stream. It's the same syntax being applied on a stream. It's also important for portability, so you can run the same query on unbounded and bounded data, and you can also run the same query on recorded and real-time data. So, and all of this basically defines the importance of why this stream and batch unification is so important. But so one question now is how can we apply this SQL semantics on streams? Well, actually, we don't really have to invent that because database systems are kind of already doing that. And if you're familiar with the concept of materialized views, which are basically just views which are persisted in the database system and used to speed up analytical queries, then these materialized views need to be updated when the base tables change, right? So there are different strategies how you can do that. You can do that eagerly whenever the base tables change or whenever you try to access the materialized view. But in essence, you somehow need to find a way to incorporate the delta, the changes on the base tables into the materialized view. And if you think about it, this is basically like running SQL on a stream of changes. So the input stream is the change log on the base relations. The materialized view is the result of the streaming query, and the streaming query itself is the view definition.
Yeah, but the distinction would be that in database context, you wouldn't expect that recomputation of the materialized view to happen a million times of a second, right? So the optimizations might be much less than what you would have to do, because in your case, the bread and butter is the update of the result every time.
Yeah, that's true. Like, I mean, the techniques that you use to do the updates would be different, but from a semantic point of view, it is certainly possible. You cannot, of course, not do everything. Also, all kinds of queries. There are certain limitations on what you actually can compute in such an incremental way, but many useful cases can be exactly computed like that. So how is it done? How do we do this? Continuous queries in Apache Flink. As I said before, we are using this concept of dynamic table, which is just a virtual concept here. And these tables are basically changing over time. And when we apply a query on when we run a query on such a dynamic table, we'll get as a return also a dynamic table, which then changes as the input table changes. So if we have a stream, we somehow now need to logically convert the stream into a dynamic table. And if we then want to get a stream out of the dynamic table, we need, again, to convert it back. And there are different ways to do that, depending on how we want to do that. So there's something like an append conversion, which means that records are only inserted or appended to the table. So assume you have a data stream and, for instance, like a click stream, and you just want to append each click to a table. You can simply say, okay, each click event that I get from a stream, I append conceptually to my dynamic table, and then I can run a query on this dynamic table. If I then apply a filter on this dynamic table, the resulting dynamic table will also just be appended. So either we append something or we append nothing because the event is filtered out. In that case, the result dynamic table is also just appended, so we can just convert that again into a data stream. There are other ways to do that, to build a dynamic table from a stream, is to use upsert conversion, which means that the records have a certain composite unique key, and then based on that key, we can update, insert, or remove data from the dynamic table. And if we go back and we have a dynamic table which is updated per key, so has a unique value per key, we can also convert that back into a stream that has certain markers depending on whether we do an update on a key or we do a delete on the key. And the most universal conversion is this changelog conversion, where we have a stream of changes, insert, updates, deletes. Updates can be represented as inserts and deletes. And that way we can, again, convert a table into a stream and back. So what kind of features are currently supported in Apache Flink 1.5.0? 1.5.0 is not out, but should be out fairly soon. So we have select from where clauses. We have group by having without windows, which are then basically, as we've seen that in the example with a simple group by query. We have time windows, tumbling windows, hop windows, session windows. So there's different ways how you can group the data based on time. We support joins between streams based on windows. So you can say I have a timestamp on my left stream, and I want that timestamp to be between a certain interval on the right stream. So you kind of like define a window based on the timestamps that you want to join the two streams on. We also support these non-windowed streams, which basically means that you have to materialize both tables completely in state. Flink has rich support for user-defined functions, so you can define scalar functions, aggregation functions, and table-valued functions. And there'll also be a first beta version of a SQL command line client, which I'll also hopefully show a successful demo later. Only for streaming, we support over windows. unbounded and bounded based on time. And on batch, we also support the full set of set operations, which are kind of like hard to implement in the streaming space.
Question. So this subset of join operations that you support, was this the choice of this subset based on what you felt you could efficiently execute in an incremental manner? Or was it based on, from an application point of view, the kinds of things you think people want to do with the real-time?
That was mostly defined by time. So, these were the types of joins that could be like more or less easily implemented with Flink. There are other joins that are rather easy to implement as a streaming application, but rather hard to express in SQL. So if you think of a join, you have like something like a currency table where you always, whenever exchange rates change and you have prices, and you always want to join a certain order with the most recent currency rate, then this is rather hard to express in SQL. But in a streaming application, that's pretty easy to express. So we're still thinking of how we can provide a nice API for that. Also, we're working there together with the Apache Beam and CalSat community, whether it's possible to integrate that with the concept of temporal tables. Yeah, so this is one thing where we still need to discuss a little bit. But we can definitely also support for the non-binary joins. There's already a pull request to also support those for outer joins. Okay, so what can be built with this like set of functionality, or also with the concept of like dynamic tables? So first of all, it's pretty easy to build like data pipelines that will just move data from one stream into another stream. You can transform, aggregate the data, so it's like a classical ETL, low latency ETL. You can also write your stream into a file system, into a database, key value store, or ingest files that appear and move them into streams. You can run classical stream and batch analytics, of course, with that, due to the nature of like unified batch and stream processing. You get the same semantics if you run the query on historic data or on real-time data. And you can also build applications that, for instance, power live dashboards. If you have a if you have a dynamic table that you materialize into a key value store, you can have a dashboard that just queries this dynamic table, which is materialized in, I don't know, Cassandra, for instance, and then move all the computation logic into the SQL query, and the dashboard basically becomes only needs to visualize the data. So I have a few example queries to show what you. Yeah.
You had said that currently what you do is every time you get a new record, you rerun the SQL query. So what is the interface to that? You generate a stream of some kind with the updated result, or you only see the last result?
So we don't. So whenever how such a query is translated? It's translated into a SQL. Into a data stream program. So and when a change comes, when a new record comes, depending on if we use the example from the beginning where we have the simple group by account query, right? So in that case, we would get the row routed to the node that handles exactly that key, and it would look up the current aggregate, would update the aggregate, like add 1 to increment the counter, and then it would send out a retraction record to remove the previous value, and then emit a new row to emit the new value. So you basically this would be basically converted into some kind of a changelog stream.
Okay, so I have to consume the stream that is the output of the continuously running.
So if you want to have this stream, yes, you can also write the results directly into a data store. So you could like put something that we call a table sync right at the end of the query, and then this would be automatically inserted into a Cassandra or database or whatever. And then you could always query the database and get the latest view of the data. So yes.
You just mentioned the dynamic table. Where you store the dynamic?
So these dynamic tables are stored in Flink's application state. It kind of depends. So it depends on the operation that you're doing, what kind of state you need to hold. If it's like a purely streaming thing, if you just apply a filter, then this dynamic table is never materialized, because you don't need to hold any state. If it's like an aggregation, like this by count query, you have an application state that holds for each grouping key the current value of the aggregation. That then can be updated whenever you get a new record. You can update the aggregation and send out an update.
So it's stored in the local?
So Flink stores the state. Flink stores the state, has different state backends to store the state. The state can either be held on the JVM heap, or you can also plug in, so the state backends are pluggable. You can also plug in a RocksDB state backend, and then this will go into a local RocksDB instance, and the state will then be held on the disk of the processing node. And yeah. So the state backends are designed in such a way that the state is kept local on the machines, exactly to provide like fast access to the state, exactly. But Flink uses this concept of distributed consistent snapshots to ensure fault tolerance. So the local state is periodically, consistently checkpointed into a distributed storage.
So the query is actually access the local state?
It's only accessing the local state, yes. So periodically the state is moved for fault tolerance, but all the state accesses are local. Yeah.
So if you have a failure of one of the nodes in the cluster or whatever, you go back to like the last checkpoint or something.
Right. The checkpoint also includes the reading position in the stream. So if you use Pravega, this would be like the reading offsets in the segments, which we'll learn about later. If you use Kafka, this is the offset in the Kafka partitions. So we move back the state and the input. So in that way, we can guarantee that the state has exactly once consistency, even though we process the data more than once. But since we're also moving the state back, the state itself remains exactly once consistent. And depending on how you deal with the output, you can also get like end-to-end exactly once.
How often do you check?
This is up to the users, but yeah, it kind of like it really depends on the application. So and on the state size. The state is checkpointed asynchronously, so the state backends are implemented in a way that we make a local copy very quickly. So depending on in RocksDB, the RocksDB state backend just makes links to the files basically flushes the current RocksDB state, and then makes links to the files, and then moves the files asynchronously in order to reduce the time that a checkpoint takes from the regular processing. Yes.
Could you also more elaborate on these 2 points that I bet you made a situation when I have multiple consumers. They are saving the state and offset, and as a part of my application, I have multiple scenes which save my data into database relations.
Mm-hmm.
What happens if one of the scenes fails? will I get in this situation only once, let's say, semantics? And how it's given, how can you make that? Can you explain that?
Yeah. Okay, so the question is, how can we ensure exactly once processing if the sync fails, right? If one of the syncs fails, so if you have multiple syncs. So as soon as one of the operators that includes syncs or sources in Flink fails, the whole job is being recovered. So that means we restart the failed task, we reset the state of the application, and we also reset the sources, right? So and then we basically continue processing, and we reprocess certain data. And the question now is, I think, we reprocess the same data, and the same data might then get written again into the sync that did not fail, right? So we are basically replaying, right? So this basically can be prevented if you're using like a transactional producer, a transactional sync that only writes when a checkpoint is completed. So that way you can align the data that you emit to the outside world with the checkpoints that you take for the overall system. So Flink supports that. This, of course, adds some latency on the output side because you can only write data when you do a checkpoint, but it gives you exactly one semantics. So there's different syncs that supports that. Another way to do that would also be idempotent writes. In that sense, you basically just overwrite what you did before. But you get this of course doesn't always work. It's really depends on the application. In that case, if you use idempotent writes, you also get some kind of weird intermediate state where some of the writes are new, some of the writes are old. But depending on the application, that might also be an option.
Earlier on, described the checkpoint sort of recovery process. It sounds like you recover the entire distributed job state together. Is that true, or you recover just one node at a time?
So conceptually, yes, but we're implementing a couple of optimizations to do that, like local state recovery, that the operators that did not fail have a local copy of their state, and only that needs to be recovered. There are certain, like conceptually, we recover everything, but there is certain optimizations. To be honest, I'm not on the latest news there what exactly is being done there, but there's lots of work being done to make the recovery as a whole more efficient and faster.
Checkpoint, or you do it incrementally?
May I interrupt with this? This seems is unrelevant to the SQL, Flink SQL that we are talking about. Probably you guys can ask the question at the very end. There's no checkpoint.
Quick answer, we also support incremental checkpoints. So, okay. So, to come back to the original topic of the talk, I wanted to show a few examples of like how a SQL query could look like that we run on a certain stream. So this is like the data from this New York taxi ride data set, which is like a public data set. We have a table here with a few fields. We have a write ID. So this basically is each event relates to a taxi ride in New York. So we have a write ID to identify the exact ride. We have a flag whether it's the start event or the end event. We have a longitude and latitude for the location of the pickup or drop off, and a timestamp, a roll time timestamp of when that event actually happened. So if you now want to compute something like popular pickup or drop off locations, then we could do that by saying, okay, we want to compute every 5 minutes for each location the number of departing and arriving taxis of the last 15 minutes. And this would be done by this query. So we would like have the component of each location. We would use something like a user-defined function here called cell ID for the longitude and latitude. So that's just like grouping the locations, the coordinates into discrete values. Then we would have the every 5 minutes of the last 50 minutes. This would be a hop window, which we would define in the group by clause down here. This basically groups all the data in every 5 minutes in the last 15 minutes chunks. The hop end function here returns the end timestamp of each window, and then we can simply do a count aggregation here.
Question. So this hop and hop end, is this like some kind of user-defined function that Flink is supporting, or is this a primitive in?
That's a primitive in Apache Cloud side. So this is not official SQL standard. You can also you can implement that in SQL also in a different way. If you like use a function here that computes it in every 5 minutes, and then use an over window to always group the last 3. But this is a little bit more convenient to define it that way. So this is like Apache Cloud side custom syntax, so to say. Another query that we could want to do is like we want to join the write start and write end events. Of course, on the write ID, because we just want to like complete the write, and then we want to compute the average write duration per pick application. We could do it like this. So the join would be expressed down here, where we first join on the join ID, and then this is like one of these time windowed joins, where we say the end row time is between the start row time and the start row time plus 1 hour. So we say, okay, most taxi rides will last as maximum for 1 hour, and everything that is not longer than 1 hour would be basically cut off and not joined, because this is an inner join. We have 2 subqueries here. One is for the start events, where we filter on is start, and for the end events, where we filter on is not start. We join those together, and then in the end we do a group by query on the pickup cell and compute the average of the difference of the time steps.
Do the input events need to be sorted by row time or event time for this work?
So this is like the assumption, like also like event time. This is like an event time attribute in Apache Flink. So the assumption here is that exactly these timestamps are not, they don't have to be exactly sorted, but should be almost sorted. And this almost sortedness is figured out by Flink watermarks.
Okay.
Basically, yeah, that's an important observation. You could also do it in theory also without these being sorted, but then you need to materialize both tables completely. This is being done in streaming fashion, where you only need to keep track of the last hour.
On that last one, if you got something out of order more than an hour, how does this behave?
The out of orderness here does not really depend on the attribute here. So that it depends more on how you configure the watermarks. So the watermarks you are defined basically. You say I have certain timestamps which are associated with each event, and then they can have different strategies how you derive the watermarks. A popular strategy is to always subtract a certain interval from the maximum, from the highest observed timestamp. So you could say, okay, if I subtract like 5 minutes, then I have a 5-minute tolerance for timestamps being out of order. If something is later than that, in this case it would be simply dropped. These records they would not be processed.
In this example, you have 2 streams, S and E, and let's say they're sorted by time originally. The result of this join, what is it sorted on?
The result of this join is sorted on. It's also sorted on the timestamps, but it might be so. It is somewhat sorted on both timestamps. So the way that this works is that, how does it work? So we would put from the stream that has the start events, we will put those always in the state and keep the state for 1 hour. And when an event from the end event comes, we would look up all events in the state. In this case, this is like a one-to-one join because for each end event there's only one start event. So this is pretty easy. But I think in this case it would always be sorted on the end event because the start event should not arrive before the end event. But even if it would also work, I guess.
But in a general case, is it sorted on the maximum time of this tool, or in general case?
So for it is sorted on it's always sorted on the maximum of both, exactly. Well, not necessarily. So the event timestamp does not necessarily relate to the actual time. So since the data can be slightly out of order, there's no strict ordering guarantee here. But what Flink guarantees is that the watermark is correct. So Flink will set back the watermark such that the out of orderness of the stream, whatever it might be, will be then correctly be processed afterwards.
So you're saying the output is not guaranteed to be sorted, basically.
It's not. I mean, the input is also not strictly sorted, and hence the output is also not necessarily strictly sorted. So the only thing that Flink needs to guarantee to make the further processing correct is that the watermarks are always behind the data that is emitted.
Can I ask you an unfair question, right?
Unfair
because
question, okay.
Your whole talk is about SQL is something familiar to people.
Yeah.
Let's have a SQL interface to this technology, right? Now, when I look at this example in this slide, it strikes me that the actual SQL that I had to write, which you've shown on this slide, is rather unintuitive and complicated, right? So have you guys considered some kind of a domain-specific language or some other way for a person who understands stream processing, who thinks in terms of streams temporally, to express a query, which can then always be compiled down to something like this? Would that be more natural?
I think it depends on from which angle you look at this. So I guess a person that is more familiar with SQL would say, okay, this is like easier to get than all these concepts of like watermarks and web functions that I have to implement. We don't have like a domain-specific language. So what Flink provides is it has like a library for complex event processing, which is a slightly different use case. So defining pattern over streams. So for that, there is something like a DSL. For common stream processing things, we haven't thought about that yet.
Yeah, and like I said, it's an unfair question. I think for the community, it's a good thing to think about because the whole point of this exercise, I would guess, is to make the adoption of this thing in the mainstream more likely, which is all about usability, right? So that's really the interesting question of what's the easiest way for people to express what they're trying to do.
So something that might help here is exactly this table API because this is more compositional. So where you say, in that case, so one thing where many people in SQL complain about is that you have like whatever, when you want to parse a SQL query, you always have to go to the most inner part and then work yourself from the inner part out or like to the outside. With this table API, you basically start, you would say here, I have two tables, I first do this, first do a filter here, then I do a projection, I have another table, I do a filter and a projection, then I join the two. So this query expressed in like in a table API query might be exactly like what you're looking for. And then it's both like translated into the same logical representation, optimized and executed in the same way.
Speaking about usability, do you provide some kind of gDBC interface for application itself? Or
Not yet. So one of the challenges here with the JDBC is also that it kind of like expects a finite result. So in stream processing, you basically get an unbounded result, depending on that is consistently updated. So there's like a conceptual mismatch between like the way that JDBC has been designed and the stream processing. What one could think about is that you basically that the query is executed, stored somewhere, and then you can run queries on the result of the query. I'm going to talk about like this usability part or later. So this is like the how to use Apache Flink if I ever get there.
It's a good hint, really.
Can I execute like this query on any of Flink node, or there's some dedicated some?
This is completely distributed, so the query would like you would try to shoot the query. So the query is compiled on the client. It's technically it's basically compiled into a regular data stream application, which is then handed over to the Flink cluster and then distributed, running distributed in the cluster.
So there's no partition information in this query. How do you decide to distribute?
Well, there's some partitioning information here. So there's this equality predicate here, and there's a group by here, which is basically telling you what you need to know, like how you can partition the data.
Okay, so you use all the hints from the query itself. There's no additional information provided by the user.
No. So one could, of course, I mean, if you would, you can. If you would know how the data is partitioned in the data stream, for instance, in Kafka, and you could leverage that information, you could maybe save a shuffle, but at some point, usually you need to shuffle. In this case, there's two things. There's this join here on the right ID, and there is a group by on the pickup cell. At latest for the pickup cell, you need to join again. You need to shuffle again, but if you know how the input is partitioned, you can sometimes like save the first one, but that's currently not supported yet. All right, so what could be done? So if we have this query here, like this hopping window query, you could just ingest from Kafka or Pravega, sorry, write the result to Elasticsearch, and then configure a Kibana dashboard to exactly represent this information. So this is then a fairly easy way to build up a dashboard. All right, now we're coming to this question. Okay, how can I use it? Well, at the moment, all SQL queries need to be embedded in Java or SQL, Java or Scala code. There's a very tight integration with the data stream API, the dataset API, so you can seamlessly convert tables into data streams or data sets. So you can also use all the libraries that come with Flink, like the CEP library or the graph processing library. Integrate that with the queries, which is nice. But of course, not everybody wants to write Java and Scala code when you want to run a SQL query, right? The reason for that is that the community so far mostly focused on the internals, like implementing operators, types, built-in functions, like lots of extensibility stuff, like UDFs, external catalog, and so on. And all of that is running at scale in Alibaba, Huawei, Uber, and all of these companies basically built their own submission system. They all built their own clients to automatically to basically just take the SQL string, have some kind of external catalog, and then execute the query. But in open source Flink, such a client is not there yet. So yeah, we have no submission client, we have no built-in catalog integration, even though we have the interfaces for this external catalog, and also just a so far limited set of table source and table sync operators. However, we're working on that, so we have like a first version of a SQL CLI client coming up. So this is actually when I want to do the demo. Do I need to make that bigger? Damn it. Is that large? So, yeah, we have basically this this client here. Can everybody read what I'm typing here? So if we just look at that, we can say show tables. This will show me, okay, we have a taxi rights table here, which is exactly the table that I've shown before. You can look at the schema, so we see we have exactly these fields. To the right.
So where is this catalog stored right now?
This catalog is stored in a configuration file, so there's no connection to an outside thing. So this is just mostly for demo purposes. But I'll talk about where we want to go with that later. Here we see like row time is some kind of time indicator type info. So this is like this time stamp, this watermark time attribute that we're using here, which is for which the query engine can or the optimizer can infer that this is nearly sorted on this attribute and that there are like watermarks for this load. So now we can just do something like we just want to show what is in there. So like taxi rights. And get the results. So this all runs now. I have a Kafka topic here set up on my machine. I have a local Flink instance running, and we're just reading the data now from Kafka.
So you are keep sending data now?
We keep sending data now, yeah, exactly. Okay. So we just get the data. You can also do like select. We just want to count how many events we receive per location. Where is start, which was a Boolean attribute, group by to cell ID. So the first one is the count, and the last one is the cell ID, and we see like the counts are now being updated. So this is like the table mode where we basically continuously update the result. There's also a mode where you can basically show how the changes are propagated. Let's see if I can.
Did you attach this to a running Flink job, or how did you get here?
Yeah, so this is like in the current version, the results are sent through a socket back to the client. This is of course not working in all setups, but I'll talk about like our plans, like how to make that like in a proper environment later. So that was like the table log mode. If we now run the same query again, we see that here now we have this additional column like with the plus and minus, which is like the changes. So we see decrease the result. Oh, sorry. Whoops. I didn't pay my part to the demo bugs, I guess. If you look at this row here, for instance, you see that this is how we propagate these changes. So we have a row which has a minus, which says this is a retraction row, where we remove this row with a count of 151 on this location, and then the next row that we get is an insert row, which then inserts a higher count to exactly that same location. So this is how we.
I have a question. When you output, do you always have that metadata that tells whether it's insert or delete, or do you do that just for when you don't have windowing?
You don't need that. So you don't need this information when you have a table that is append only. Like if you have such a time window query, like a tumbling or hopping window, then if you only emit complete final results, then you don't need this information. Then it's like the result table is an append-only table, and then it's basically only inserts.
So where to read that metadata? Is that like a metadata attached to the output event? Is that how do you propagate that to the sinks?
So whether you need it or not, or
how do the sinks interpret that?
Okay. So when you this is basically a Boolean flag. So each row is then wrapped in a tuple with a Boolean flag and the row. This is how we encode that. Yeah. So this SQL client is a nice tool to play around. So you can run certain queries against tables that you have configured. So, all right. So. All right, you've already seen that. That's a nice toy, but can I use it for anything serious? Well, I guess this exact version, not yet. But we're working on that. So the plan is to basically implement a REST service to submit and manage SQL queries. This service will be able to submit to execute select queries as like the ones that we've seen before. Queries where we do insert into select, basically where we directly write the output of a query into another table. That could be then some kind of a file system or an event log or whatever. So we can directly write the result of a query into some kind of data store. Or we materialize the result, write the result as a materialized view to some data store. One big component of this will also be like serving the results of these select queries. So the latter two cases here are not that hard to implement because you're basically directly writing the result into some kind of data store. Whereas if you run a select query, you typically want to get the results back, which is a bit challenging in a streaming environment. Also, this service will integrate a table catalog. Also integrate with external catalogs like HCatalog or the schema registry. And the use case for this service then can be like data exploration, so you can connect that from a notebook like Apache Zeppelin. You can access these real-time data from within an application, or also build a simple console to run ETL jobs and move data from one place to another. A big challenge, I said that before, is like how do we serve the results of these dynamic tables? Because these results are unbounded. Unbounded input yields unbounded results. There's different cases. So there's this like append-only case where you just do a simple filter here. And there is the continuously updating case where we do a group by query with a count which is continuously updating, where we have to basically retract results that we've previously emitted. So the append-only table, the result rows are never changed. So there are different ways. So either the options, so either the consumer keeps on consuming the records if the consumer cannot keep up with all the results. So imagine if it's like a small application, if you're consuming from a large stream, then the query would need, or the query executor would need to buffer the results and maybe at some point also drop rows if you cannot keep up. How you exactly do that is, of course, up to the user. Well, needs somehow to be configured. If we have this continuously updating table, then there's different options. Like the consumer could just consume the changelog stream that is maintained, or the result table must be maintained somewhere in some kind of data store. So you can think of the executor has some kind of data store configured, like a database or a stream store, where the results are routed into, and then later can be fetched back later from the client that submitted the query. How would that look like? So here we would have like some kind of query service, which has a REST interface and a catalog, the optimizer, and a component to serve the results. This would be the Flink cluster. Here's the application that submits a query via REST. Then the query is accepted by the REST service. It's optimized using the information from the catalog. The query is submitted to the Flink cluster, and then runs in the Flink cluster, consuming from an event log or from a database or HDFS, depending on what exactly the source is. It would then write the result back into some kind of configured event log or database, which then could be read from the result server and sent back through REST to the application. In that case, like all the results would be served via REST from the query service. So the application all of that can be done with REST calls. However, this works well in many network configurations, but of course, like this component here can become a bottleneck because you're routing all the results through this query service.
So that is, you can easily distribute that query service because there's no connection between two queries, right? So
no, that is true. Yeah, you could scale that out as well. Yeah. Another alternative design that we're thinking about is where we do exactly the same thing, but instead of returning the result, the query service returns back a result handle, which then can be used from a serving library, which then like integrates, for instance, like a Kafka driver or a JDBC driver, which then fetches the result directly from this. Yeah, so all of that is not yet cast in stone. So if you have valuable feedback, we're really looking forward to gather user feedback. What kind of scenarios would be useful? What kind of how would such a component be used? If you have a use case or feedback that you think would be valuable, please share it with the community. All of this has not been implemented though. So this SQL client that I showed like first step towards this design.
You spoke about Calcite being your language surface. Do you have plans of adding Beam SQL to? I noticed the Beam sticker on your laptop. So.
Well, Beam SQL also uses Apache Calcite. That will come like just naturally, right? So we have there is a Flink Beam runner, and I haven't tried it. I assume that if you just would run a Beam application that includes a SQL query, that would just compile down into. So I've looked at the design document. So to me, it seemed like when you specify a SQL query in a Beam pipeline, that will be translated into a sub pipeline in Beam, and then it should be just executed as anything else. So
is it the same as Calcite, Beam SQL, or is it other modifications?
So to my knowledge, Beam is also using like the syntax provided by Beam. Yeah. Okay. I'm at the end. I made it. Summary. So unification of streaming batch is important. Flink SQL addresses many use cases for running SQL queries on streaming batch data. It's running in production at several big enterprises, and the community is working on the user interfaces to make this more usable. I also have a few announcements to make. So there is going to be a Flink conference in a month or so in San Francisco called Flink Forward. We have a pretty good lineup of speakers at this conference. Yeah, so if you're interested in learning more Flink use cases, talking to Apache committers, to Flink committers, or users, come there. We're waiting for you. Yeah, thank you. This is the book that I talked about earlier which is making some progress, but not that much.
It's not written yet, right?
You can get it on early release. So, so we have like about 70% of the chapters are done now. Right.
Time for another question. Okay. I gotta say, this is super cool. What you're doing is really super cool. I love it. If there's one comment I can make, given what you're trying to achieve with this, whoever you and the folks in the community are working on the SQL thing, I think the exercise you need to do is go end to end, which is if I'm somebody at a company and I want to use this to get like streaming data from my sensors and produce a dashboard for my management that they can go to anytime and look at, what are actually all the steps that have to be done? Because some of the stuff about get the data back from the result and incorporate it into my UI and all sound to me like they would be, although intellectually not as challenging or appealing to solve, from a business point of view, equally important problems to solve. To really have the right effect, right? So it's just something to consider.
Yeah, that's very good feedback. I've said that before, like until recently, we pretty much focused on the internals, on the operators. We also like a little bit driven by the users that we work with, from Uber and Alibaba, who like built their own submission system. So now we're trying also to catch up and build something in the open source version.
There is one announcement. There will be one free Flink Forward conference given away at the end of this session. There will be a question. Whoever answers that question correctly will get that.
I thought the prize was for who asked the most questions. Come on.
So don't you guys have the bio break or?
Flag to show up. Steve and I made it to the sound.
Did you? The one where we lost?
No, the one where we won.
Oh, the exhibition?
No, I thought it's like the Champions Cup of America.
Oh,
right?
it's a Champions Cup.
Yeah.
We won. How did we play?
It was like Guatemala or whatever, their name, I think, or Ecuador, I'm sorry, I'm butchering it, but it was, let me produce name, Eklas something. Yeah, I think his daughter was out or whatever, and so I took her seat. Oh, his seats are sweet. They're like penalty box, like 10 seats. Like 18, is that the 18-yard line or whatever? Not halfway, right?
Oh, 18-yard line.
18-yard line, yeah. Sure. Pretty sweet, like 10 seats now. I mean, really great seats. So, yeah, we watched it. I mean, whatever. It was a good game. It was they scored quite a bit. It's like 4-0 or something. But those guys were dirty as shit. Like that Tampa team. Holy crap, man! These guys are either on the ground or just arguing and just annoying the referee. He was pissed.
You expressed something.
The ref wasn't. I think they got specifically someone who was very. He was. I mean, like the game started, it was already like 4 yellow cards. So they kind of got the point. Like if there was a softer referee, they would take advantage of it. So he was very quick to.
Well, they want to snuff out the game away and win the game.
Right. And they had already lost. Founders had lost 2-1 away. And so they just need to kill the game. And so it kind of there was a dramatic shift, right? When Sounders scored their first goal, so now it was the other way. It was just now the Sounders are all like, got in the corner post.
That's right.
But at the end, they kind of ran away with it. The quality of
it was a very simple problem.
It was not competitive. I mean, they did win. Right, they won away, but here it was pretty, yeah.
The two things I would say about that, just
it was about, I would say, from capital. It was not a significant. I think what might have been more impactful was actually, for these guys, they were all wearing, the stuff underneath and the gloves and all this. So that might have stiffened them up a little bit.
Very unusual for them.
Right, they're coming like somewhere. I don't know exactly where, but warm stuff. And so that was probably a challenge.
The more you put intermediate things to materialize,
that was fun, man. I have played a Sounders game for a long time.
Yeah,
because you're making the plan more and more explicit as well.
Well, yeah, where you live, I guess you can do it. For me, it's such a dream, right? Like, I literally got on the train for 2 stops afterwards. And was gone. And getting there just wasn't.
It's globbing it all together.
It's right by the base.
So is this better than Henry's?
Yeah, they have an open beer garden. Yeah, they have an open beer garden in the summer. It's literally across from the statue of who's that?
Things like that.
They have a lot of customers.
Like,
That's fantastic.
Jealous.
Maybe limited as well. So
yeah, we gave up our Sounders. We go to the ladies.
At the end of the day, if you were dissatisfied, usually that needs a
The
power.
ladies soccer. They're the rain. I got
And I'm super stoked.
They're covering more of SQL than I have. I was skeptical about how much of joins and stuff. I gotta say.
Where are they going to play?
Play the Starfire.
Wait, indoors?
The link is like everyone has their version of Link.
Yeah.
Starfire is like
That's the beauty of SQL, right? That the primitives.
Yeah, but I only thought they go to
no, you can Starfire. They have like
and what about the
4
rain?
fields.
Okay. I kind of like I've played like small leagues here in Seattle. That's what we play on.
Sort of like that, but it has stadiums. It has absolutely.
So there are some bleachers.
Not as big as like the Brown stadium, but
it's 10,000 or something.
Top really
Calcite, these guys
a little bit bigger than
this duality between the table representation and street.
For a while.
Yeah, just excited because the chance to support.
You're basically incremental query
that game is fun. I don't know shit about it. And I did one game, but I was fun to watch. No doubt.
But as little of it.
It is hard to follow.
They must be like some
didn't grow up so it takes some. I'm just trying to commentate on everything that's going on.
Okay, and where is it?
It's going to be Starfire is
Generation.
Ooh, that would be a trip too. I mean, I don't presume they'll be easy to get to and go away because it's not that.
I'm not introducing you. You get to.
They'll clog you up.
8,000 people is not a lot. Not compared to what you just.
Probably. Oh, that was probably about 15 to 20,000. About half full on the lower sections as well. They have not obviously.
All right, is this thing working? Yes, it's working. Yeah. So hello everyone. So thanks everyone for stay. I know it's a bit late. I don't really need to fry your brains at this point, so hopefully it's going to be a light talk. But feel free to ask questions like you just did to Fabian. So today I'll be talking about Pravega, and you're probably wondering how is this related to Flink, given this is a Flink meetup. And the reason why we talk about it here is because we're doing a lot of the work we're doing in Pravega targets a connector that we have for Flink, and so we're trying to make it a very strong binding between the two projects. And we have been working very closely with Fabian and the folks in Berlin, and this is ongoing work, and we'll keep being like that for some time. And so I had the privilege of being part of the engineering team developing Pravega and leading it as well. And so I'll go and give an introduction. What Pravega is, in just one sentence, is a system for storing strings. Our main goal is to develop a system that has strings as the main primitive that we are storing, and make it a first-class system for stream data pipelines. Make it very efficient for stream data pipelines. It's a young project. Some active development. We have been doing this for the past. Hasn't completed 2 years, but over a year for sure. And it's already open source. So we have a website and we have our GitHub repository. If you're interested, feel free to go check and interact with us. Before I go into Pravega concepts, let me cover a bit of the basics on streams. Might not be necessary for this crowd, but just so that we are on the same page. Yeah? So when I talk about streams, I'm thinking about applications that are, in the space of social networks, online shopping. Users are generating events out of status updates, tweets, whatever they're doing their online network. Also, if they're shopping, when they're purchasing stuff, when they're browsing and looking at things. So those are events that you might be interested in processing. But it's not only about end users, right? So we can also think of streams that are generated by machines. So if we're monitoring a fleet of servers, they can be generating, CPU utilization samples, memory utilization, disk utilization, and so on. Those are also streams that we might want to process and get some meaningful insights out of it. One special case of this that it's very interesting these days. People talk a lot about it. Is in the IoT space. Sensors. If you have devices emitting like temperature samples, or even in connected cars, all the sensors you have in a car emitting those samples that you might want to store and process in the form of a stream. So those are examples that, at least when I think about streams, that come to mind. But then, so I mentioned that Pravega is about storing streams, and I mentioned this example of streams, but what does it even mean to store a stream? So what should I do differently if I'm storing a stream? One thing is, a lot about a stream is about order. Right? So the order in which things happen. So if I'm talking about, social networks, online shopping, and so on, so the order in which things happen might matter, because I might want to answer questions like, has event A happened before event B? Or how often people purchase X and then they purchase Y? Or even if I'm doing some form of a window aggregation, how many people visit a particular website every hour? Right? So those are all sort of questions that we might want to answer, and if we preserve that order for the events of a stream, it's a lot easier for me to process the data and make sense of what I'm doing. Looking a bit more closely at how I see a stream, we have at least three parts, yeah? So we have present, all the stuff that has gone into the stream. You have recent past, which could be, seconds, minutes, days even. It really depends on what recent means for the application. But recent meaning that it's stuff that you care about and it feels fresh for you. And then you have all the stuff that still belongs in the stream. They have ingested like a long time ago, but it's not really in your definition of recent. So all that can be part of your stream. And today, what we typically do is, this recent pass is stored in a messaging or a pub substrate. You can think, of RabbitMQ, Kafka, that kind of stuff. And the distant pass goes into some bulk store, maybe HDFS. Right? So those, we would store our stream data that way. What we want to do is to actually converge that. So we want Pravega to be a system that is actually storing all that for you. Not only the recent data, not only the distant past data, but both, so that it can process different parts of your stream as a stream anytime you want. But it's not only about that convergence. There are other things that we want to do as well. Like, we know that it's particularly important to deal with the variations of ingestion rate. Right? So as you have daily cycles, seasonal spikes, all that kind of stuff, you might want to adapt the capacity you're giving for the ingestion of a stream. You might want to adapt to those variations. And so we want to do that. And also, because this distant pass can be really distant, right? It can be like a long time that you have been accumulating all that data. We need to be careful in how we design this so that we can accumulate an unbounded amount of stream data. So those are all important concepts. So if I have to summarize some target points for Pravega, so Pravega is primarily a stream store where we aim to store stream data permanently. Permanently in the sense that as long as you want to keep that data, the data can live in Pravega. You don't have to move your data from one storage dependency to the next. We need to preserve order to be able to answer some of the queries that I was referring before. And we want to accommodate, so not only store that data permanently, but also we need to be able to accommodate an unbounded amount of data, because as data comes in, it can come in for a very long time, and I must be able to accommodate all that data that is flowing. And we want to do that adapting to varying workloads, right? So as we have spikes, daily cycles, seasonal spikes, and so on, we want to be able to accommodate those changes and vary the capacity that we're providing for the ingestion of data. And finally, because it's stream processing and lots of applications have latency SLAs, we really need to provide low latency from append to read. So those are our goals, core goals that we have in the design of Pravega. Okay, so streams in Pravega. The very basic is we ingest stream data by appending data to a Pravega stream, and we process stream data by reading data from a Pravega stream. When we look closely at what a stream is, it's a composition of segments. So a segment is a stream unit. It's an append-only data structure that stores a sequence of bytes. So that's the unit that forms a stream in Pravega. What can we do with it? Well, so one thing that we can do, and has been done before in other systems, is to provide parallelism. So as I'm ingesting data, instead of using one single segment, I can have multiple and have the application writing to those multiple in parallel. And I can have actually many of the things writing in parallel. So I'm giving more capacity for ingestion. Now, how do you actually decide which segment the append is going to go to? Well, that's based on a routing key. Right, so that routing key determines which one of those segments is going to take an append, and so the same routing key is always routed to the same segment. One thing that we do that is interesting is that we can seal segments. When we seal a segment, it takes no further appends. Right, so no appends go to that segment anymore. So essentially, the data is fixed for that segment. But then you're probably asking, okay, so how's that even useful to me, right? To seal a segment, how's that even useful? Well, it's useful in a number of ways. For one thing, I can take two seal segments, concatenate an open segment inside so that I can append into this open segment and call that a stream. I can go even further and concatenate an arbitrary number of those sealed segments, in which case I can store an unbounded amount of stream data, which is a goal that I had, and call that a stream. So that's something you can do by manipulating the segments. But it doesn't have to be on linear composition, right? So I can put two seal segments in parallel, an open segment, and also call that a stream. But okay, so this is perhaps an abstract way of seeing the segments and how we can manipulate them, but what are useful features that we can actually do by doing that kind of manipulation? One that you might have guessed at this point is scaling a stream. So if my stream starts with one segment, this is just for simple purposes. You can have as many as you like in the beginning here. If Pravega declares it to be hot, I can seal that segment and create two new segments. Right, so I can seal and now create two new segments that will provide more capacity for ingestion to my application. And if now I take that concept and try to analyze a bit further what kind of dynamics I expect to have for a stream, so what I have here, what I'm illustrating here is time. So this is the behavior of a stream over time, and this is the routing key space. So if I start again with one single segment, I can decide that at time t0, so that segment needs to be split, and so I do it in two segments, 2 and 3. Later on, I decide that 2 is still hot, so I split it into 4 and 5, but 3 is fine, so I leave it like that. And at t2, so these two are kind of cold, and so I merge them back. So this is the kind of dynamics that we expect to see with a Pravega stream. one interesting point that you might have noticed is that now the mapping of the key space range, any given point in the key space to segments is actually changing over time. So it's not fixed. So as I make progress on this string, I'm actually mapping different points to different segments. And this is something that Pravega takes care of. So this is the kind of complexity that the application is hidden from the application, but allows the application still to have this kind of behavior. Now, to make this even more concrete, this is a heat map that we have taken out of a run in a Pravega cluster. And so what we observe here is splits and merges of that string. So the white spaces represent the separation between the segments, and the colors represent the state of a segment. So light blue means that the segment is lightly loaded, and bright red, it's not so bright red, but so my screen it is. So this is supposed to be bright red, and that represents very heavy load on the segment. And so what we're seeing here is actually a stream where we are slowly merging segments up to the point of a minimum, and at some point it starts splitting up again. It almost feels like traffic is dropping here, is at some level, and then it's dropping down to a minimum around this time, and then it starts to pick up again. And this is exactly what we're saying, right? So we use the same data set, the same New York City data set. I don't know why it doesn't show up here. Okay, this is supposed to be 4 a.m. This is exactly the behavior same, right? So we have the workload here, slowing down to a minimum, and then picking up again. If I put those two charts together, this is exactly what I'm saying, right? So while we have, while the workload is too high, we have enough segments. As it starts to drop, Pravega goes into merging segments. When it's at a minimum, it goes to the minimum set of segments that we have set, which was 2. And as traffic starts picking up, then it goes into splitting segments, and we get to the state of the string. All right, so this is outscaling in Pravega. This is illustrated outscaling Pravega. The next feature I want to talk about the leverages effect that we can manipulate the segments is transactions. So we also allow you to do transactional writes, where the idea is that a batch of writes is either made visible jointly, all of them, or none of them. And the way we do this is by creating transaction segments. When you begin a transaction, Pravega creates those transaction segments, and the writes go into those segments. It doesn't interfere with the traffic of the main segments. So I can still have writes to the main segments of the stream, and again not interfered by the writes to the transaction. And this is very important for exactly one semantics. This is one of the features that we actually use with Flink connectors to make sure that on the same side we output all or nothing. To say a bit more on what the flow is for transactions, let's say that let me give this example where I have a stream with 2 segments. When I begin a transaction, I create 2 transaction segments for that stream. All the writes in the context of the transaction go to the transaction segments, like in steps 3 and 4. And when the application is ready and it commits, the segments are sealed, and then they are merged into the stream segments. And only then that data is visible. And this is nice for a couple of reasons. One is we are not interfering with the traffic on the segments of the stream, right? So again, the writes to the transaction are going to the transaction segments. And so if you want to do writes on those primary segments, it can go without a problem. Nothing's blocking it. And in the case the application decides, instead of committing, if it decides to abort, all we have to do is to discard those transaction segments. And there is no trace of the data. It never interfered with the primary segments of the string. All right, so those are 2 features that we have implemented that leverage this ability of manipulating segments. Now, let me talk a bit about how we implement it internally. So internally, Pravega is a combination of a control plane and a data plane. So the control plane manages segments. It matches segments to streams, creates segments, tells segments or to merge segments, and so on. It also does transaction management on behalf of the streams. And anything that has to do with the segments themselves, it commands the segment store to do. The segment store, it doesn't understand streams. It understands segments, and it stores the raw segment data. And it does all the hard work of making sure that the data is available, that the data is consistent. So one way of depicting what Pravega is like this: a repository of sealed and open segments that we make sense in the form of streams and expose to the applications, that is implemented as a combination of a control plane and a data plane. All right, so I've talked about, just to do a bit of summary of what I have talked about so far. So we have seen that Pravega deals with segments. It has a concept of segments. It manipulates segments to form streams. Then I discussed two features that we can implement with that, and I talked about control plane and data plane. Now let me move on to the API and tell a bit about how we actually use Pravega, how an application is supposed to use Pravega. Internally, Pravega stores bytes. It doesn't understand any other abstraction. But for the application, to make it easier on the application to use it, we expose the concept of an event. So we have event readers and event writers. Now, we require that the application provides a serializer, so that whatever events we push into Pravega, it goes into it's transformed into bytes, and then on the way out, the other way around, so get the bytes and transform them into events, so that the application can process it. To get a stream writer, so to write events to Pravega, we first need a client factory. So with the client factory, we can instantiate a writer. Once you have a writer, you can just go into writing events based on whatever source you know it's interesting to the application. So those writes can also be transactional. So from the writer, I can begin a transaction, can do a bunch of write events, and I can finally commit. To see what happens on the write path, so let's have a look at this diagram. If the stream writer has never is the first time that it's writing to a given segment, you will need to locate the segment from the controller. This is the case because you can have multiple instances of the segment store server and needs to determine which one it has to talk to. So once it does that, it can start appending bytes to the controller. To the segment store. On the segment store, we'll write to tier 1, which is currently implemented with Apache ZooKeeper. And you won't acknowledge to the writer until it gets an acknowledgement from ZooKeeper. So the data is made durable before we respond to the client. And asynchronously, we write the data to tier 2, which is our long-term storage. The reason why we have these two storage dependencies is because on the write path, we wanted to have a durable, low latency option. While we wanted to have, at the same time an option that gives us high read throughput for catch-up and historical processing. So ZooKeeper wouldn't give us that option, so we opted for having a second dependency here. And so we implement a few bindings. Actually, one thing worth mentioning is that the bindings here, so we can implement multiple bindings right now. So we have one HDFS, NFS, and an extended S3, which is one of the options that we want to support. And so this can be extended to other things. Like we have implemented changes so that we could also use, for example, Apache ZooKeeper so that you could have one single dependency. So this can be extended. Yeah.
So speaking about storing to HDFS, like how do you store segments? And if you store segments as an individual file, how do you resolve issue with having multiple small HDFS files?
So we don't have, so we have files per segment, but we accumulate a lot of data per segment. So we do not have many small files.
Like, so you was talking about segment as a piece of stream.
Yeah, but that can live for a long time. So that can live for several minutes, and that can accumulate a significant chunk of data.
Okay, so how many segments do I need to have in my stream? Like, how do I decide?
It's up to the application. It's up to the application. You can start with a number that feels reasonable. You can start with 1. You can start with 10. You can start with 100, and just let Pravega do the auto scaling.
I'm trying to understand like the idea of these segments. Like, is this something to do with partitioning? Like, should I choose number of segments depending on my partitioning schema, or should I choose it depending on like my window duration, or should I choose it depending, like, I don't know, randomly or whatever?
Right. So the initial number of segments, because so there are two options. You can have a fixed number of segments, in which case you decide that I want to have 10 and you always have 10, or you can let it auto scale. You can also manual scale, but let's put that on the side, yeah? So you can auto scale or have it fixed. So if it's fixed, then you have to make your calculation beforehand. Otherwise, you let Pravega do its auto scaling thing. But now the way you compute it is based on your capacity. So you have to determine how much parallelism you want on the stream, based on your expected ingestion rate, and that's how you compute the minimum number of segments that you would like to have. Because if you remember the figure that I was showing, we had configured the stream to have a minimum of 2. So even when we got to the bottom of the lowest level of the workload, you still had 2 segments. We could have configured that to have 100, and then the minimum would be 100, right? Again, so that depends on the level of parallelism on the degree of parallelism you want to have for ingestion.
So what's wrong with the mental model that just start with a small number of segments, like 2 or something, and then let the auto scaling do what it needs to do?
Yeah, that's what I was saying. There's nothing wrong with that. So you can do it and let it scale.
Flavio?
Oh, sorry. Yeah.
So my experience is that this model breaks if you have a lot of consumers. Because if you have like relatively long-running consumers, then you need a lot of, you cannot have more than 1 consumer per partition, right? And then you practically you are forced to have large number of partitions. Then you have a lot of small files. You end up with practically a lot of like performance problems because of that.
No, because we auto scale and we merge them back. If you have very cold segments.
But if you have 50 partitions, 50 consumers.
If you have 50 so what? Okay, so
you are forced to have at least 50 partitions, right?
No, these are not partitions. That's what people are getting confused.
So you can have more than 1 consumer for a partition.
Okay, so in the same read, I haven't talked about readers yet, right? But well, maybe we should wait until I go into that. Yeah. All right. So what kind of guarantees we provide on the write path? First one is order. So writer appends following application order, and we guarantee per key order as per the observation on the parallelism I was making earlier. We avoid duplicates by using writer IDs. So each ID has a unique ID that we persist on the segment store side, so that we know in the case of a reconnection where to resume the writes from. And this, along with transactions, enables us to have exactly once on the write path. So we do, again, the duplication based on the write IDs, and we can have atomicity for groups of writes using the idea of transactions. So even if you crash and you are in the middle of a write, you have a partial write, then so that can be aborted or timed out. So Pravega times out automatically.
It's a batch process.
The reader, so getting a reader instance is pretty similar to how we get a writer. One difference is that we force a reader to belong in a reader group. And once you have that, you can go into into a loop and reading the next events. One important observation to make is, along with the events, we provide the position of a reader. So it's in best interest if the application can do it to save that position, so that in the case it needs to resume from that position, like if the reader crashes, that it can give it back to Pravega and let the reader group resume from that position.
What's the semantic of reader group?
What's that?
What's reader group?
So reader group is, hold on to that question, it's just right now. So the read path, on the read path, so when a reader is getting, is reading data, the idea is that it gets data from the segment store, from the cache of the segment store. If it's a cache miss, then you will read data from tier 2. Now, we never read data, we never serve data from Apache ZooKeeper. So in Apache ZooKeeper, so the data in Apache ZooKeeper is there for recovery purposes only. Now, so reader groups are groups of event readers. So it's a collection of readers that we have put together to serve a set of streams. So we tell it what set of streams it wants, so that group is supposed to read, and the internal logic of the reader group distributes that load across the readers of the group. And that load is comprised of segments. So a given reader will read from the segments that it has been assigned to it. Actually, it picks the segments from the set of available segments. And that coordination happens via a facility that we provide called the state synchronizer. So the state synchronizer is a facility that we provide via our API, and we also use internally. It uses a revision Pravega segment, which gives us essentially consensus power by allowing us to do compare and swap, compare and sets on a Pravega segment. Let me go through this illustration to show show the operation of a reader group. So say that I have a string with 2 segments, and I have a reader group with 2 readers. So the top reader is reading from segment 1, bottom readers is reading from segment 2. At some point, say that the stream scales. So the stream scales, and now I steal segment 1, and I create segments 3 and 4. So the top reader is unaware of that at this point. It's still reading like the second event here. It hasn't gone to the end, so it keeps doing its thing. Same for the bottom reader. It's reading from segment 2, and that's all good. Eventually, the top reader will find out that segment 1 is sealed, so it's going to go to the controller, request the successors, and update the reader group state. So we'll make those segments available for reading, and from that point onwards, those readers can pick the segments. So now those 3 segments are available. Segment 2 is still assigned to the bottom reader. The top reader didn't have anything assigned, so it picks segment 3. Segment 4 is still unassigned, but the bottom reader may decide to pick it up, in which case the assignment we have is 3, 2, and 4. The assignment is not necessarily like that. I've done it this way to illustrate that it's not necessarily the case that the top reader would pick segments 3 and 4, because otherwise I would have the problem that if I keep splitting up, I could overload that reader. And so the segments are made available to the reader group, and they pick up depending on the load they have.
I have a question. So if it's dependent on is there any way to force that the key range that one reader had would be the same? Because if you're talking about, what you just said there, another reader group or whatever, taking it into taking over something due to load balancing. For a stateless computation, that might be okay, but for a stateful computation where you need the same key, how would you deal with it here? Is there a way to force that?
No. So by design, we avoided going down that route, because as we're splitting and creating new segments, we wanted to distribute the loads of segments. Right. So,
are you guys thinking of ways to do it in a stateful manner that could guarantee this key range thing, at least for a reader group or something like that?
Flink actually has this problem. If you connect a Pravega to Flink, Flink is aware of key space range, right? Because it wants to send queries to particular points. We actually mirror that and hook into the same mechanism that they have with watermarking. So, and they have the watermarks and the checkpoints that happen at regular intervals. So the idea is that you also at Pravega have checkpoints that you can initiate, and the readers will receive them, assuming you initiate them. So if you're using Flink's checkpointing mechanism with the Pravega, it'll cause Pravega to issue a checkpoint. The readers will see the checkpoint, see the checkpoint ID, and it's only at that point that the segment will be transferred can be transferred off of one reader onto another.
I see. So you're saying there's kind of like a synchronization where if you had a Flink pipeline that was reading from reader 2 for a certain key range, at some type of synchronization point, you would realize, you would take your checkpoint or something, then you would realize that, hey, this key range might map to a different reader, in which case I'm going to start reading from there. But doesn't that get a little bit hairy, because what key range are you actually looking at that point? Like, how would you know where it maps to in the new world? Because it seemed like that blue square changed from one guy to another guy. How do you know what unit that is? Like, how would you know where all the keys that you care about are without Flink itself maybe scaling or I'm unsure.
Well, it doesn't have to scale. I don't know. So Fabian may confirm this, but my understanding is that as the source tasks, maybe this is a discussion for after I talk about the connect. I don't know, but let's try to sort this out quickly. So as the source tasks send the events downstream, right? So that sorting of keys is done at the operator level. Yep. So you don't need to do that at the reader directly.
I mean, so what I'm saying, very very simply, you have a group by device ID. You send device ID, and now let's say your Flink topology. I don't know what the topologies look like. It could be partitioned by 2. The one guy has one reader group. The other guy has the other reader group, and one set is dealing with a set of device IDs. The other guy is dealing with another set of device IDs via, let's say, a random hash partitioning, not necessarily range partitioning. So then your reader group needs to scale up or something like that, and then something that, if it's a hash partitioning, I really don't see how you could do it. Like, how could you do your stateful computation without some type of global sync at the end without...
Yeah, I get that. But we stepped away from that world sort of on purpose.
Sure, I was wondering how Flink interacted with you to potentially provide it. Because you're basically making it so that the application or the user of Pravega needs to deal with it. I'm just interested to see how Flink did deal with it.
Flink does shuffle it.
What was that?
Flink does its own shuffling, right?
Yeah. So you're forcing a shuffle then.
Yeah. So you would
practically they do force it.
I see. So you force a shuffle. Okay. I see.
So you don't rely on the partitioning coming from the source.
I see. So that answers it. So if you force a shuffle, then you don't need to do any smarts. You just force the shuffle, and then you got it.
But then you don't benefit from the load rebalancing.
Right? You do.
Well, you do.
You do, because if I'm splitting the keys, like what's happening here is I don't know. So if you see, to simplify, it was 50-50, right? And now I am autoscaling, so I'm splitting 150 into 2 new pots, right? So one part is coming to the bottom, and the other is going to the top. So you're still able to benefit from scaling.
If you shuffle, as long as you shuffle, you can take in. It just comes for free. I mean, it's not free. There's a shuffle, but once the shuffle occurs, then you're decoupled, right?
Yeah,
decoupled from
exactly. But if you wanted to do that directly on the reader, without doing the shuffling, then that wouldn't work, because essentially this is static world that
But then once you do shuffle, you've lost the distribution, right?
You lost the distribution? What do you mean?
Which dimension are you shuffling? Like, let's say group by device ID. Which dimension are you shuffling?
Yeah, it depends on pipeline.
So what?
So it's by key, right? It's by key.
So the key,
Okay.
the key in Pravega is the main purpose of the key in Pravega is to ensure that the data stays in order with respect to the key. It's not about like distributing the data. It's only about like keeping the data in the right order. So all records that have the same key that are written to Pravega will always go to the same segment. If you split a segment, they will all go to the same splitted segment. So it will stay in order. So that's basically what Pravega is.
Yeah, that's something. Oh, is that what you're referring to? Yeah. So that's something we guarantee. So that's part of the reason. Okay. So in this example, it's a bit easier. But if you're merging, for example, it's a bit more complicated because we need to guarantee that order that Fabian just mentioned.
But what about the case? How do you guys handle the really hot key scenario where like 90% of the data, you had a 10x increase, but it's 90% is one key? How would you guys deal with that?
Yeah, so in that case, if you have to split up to the point that a key is in a single segment, and so that's the maximum we can do.
Can you auto scaling the reader also, or the when the segments auto scaling the reader just keeps saying?
Yeah, so yes and no. So we don't scale automatically for you, right? But we do give you signals that you need to scale. That's actually some interesting work that we are doing with the Flink community to get it to work, because if we scale but downstream you don't, then there's a much benefit. You have to scale end to end, right? So that's one thing that we are working on. So we give the signals, right, that any application, including Flink, can use to determine when you have to scale a job.
Okay, so like say if I get signal, I go to even manually scale that, so the reader will go to ask the controller again to get the right read from right segments, right?
Yeah.
Like say now we have like in this example, after the auto scaling, you have 3 segments, 2 reader. Like say I get a signal, like say my reader is slow, and I want to add 1 reader even manually. So it will trigger the kind of rebalance of the reader. Kind of, right? Then the 3 reader will read from 3 segments.
Yes,
That's true.
Okay.
That's how it works. It gives the signal, so the program will automatically can handle it.
Okay. Because you have the
Flavio,
together.
question for you. Going back to the single hotkey question that was asked earlier, right?
Yeah.
So, as distributed systems guy, I would ask you, are you just referring to a generic concept, right? Any database, any scale-out table thing anybody's ever built, right? Any storage system, the simple technique you use is you partition the key space across your servers and you handle the load. And that's one level of complexity. And then if you really want to deal with the case where a single key is hot, you have to introduce a whole new level of complexity because you've lost the simple parallelism of the partitioning, right? And what you're saying is, in the case of Pravega, like some of the systems, you've chosen not to go to that second level of complexity, like what happens if I have one really hot key?
Well, we're trying to provide order per key. So that needs to be serialized anywhere or somewhere.
Somewhere or the other, you'd have to do that. Yeah,
yes.
Exactly.
So you have to sacrifice something there. If you decide that you don't want per key order, then maybe you can parallelize the work of a single key, right? But to preserve that order, we need to just to have a sequencer somewhere, which today is a segment.
And then there is no limit on the number of keys.
Yeah.
You can have as many keys as you want.
But
yeah.
You can separate sequencer from the partition, from the segment. You can technically have one sequencer which puts into multiple segments because it's practically single node which does a memory operation.
You could, but you still have a bottleneck, which is a sequencer, right?
But is that a good answer to your question, that you can just have more keys? Like, what's the application scenario where you'd really be bound to having only the one key?
No, I mean, I think if you think about it simplistically as just the data movement, then maybe you can have more keys. I'm talking. If you start to think about grouped computation and/or like really when you're processor bound with merging everything together from all these keys, I think it gets a little bit tricky. I mean, just these what are they, Zipfian or whatever distributions are very common. Like there's a hot user, 10 million likes, 10 million whatever. I mean, these things break Twitter, they break everyone. The only work I've seen for splitting that somewhat made, there's 2 lines of research that I've investigated. One is adding some type of layer of indirection in between where you can sub-key it, but then transparently transparently bring it back together. But that was in the, it's not just splitting it, it's splitting it and doing some type of pre-aggregation and then doing your final aggregation kind of transparently to users. The other is taking into account when you split the downstream computation. That's out of the realm of something like Pravega, but something that a tight integration with Pravega or Flink or something, I would be interested to see what even the APIs would look like for that. But, yes, you can always say sub-key it, but it's not, I mean, there's definitely a lot of problems. You have a key, and someone's going to need to do the merging. At the final end, you're going to need to merge it, regardless of whether you have the sub-key in between or not. Right. I'm more concerned with the end-to-end answer, not necessarily the Pravega layer necessarily, but all of it together.
Your first solution is exactly what Max proposed, right? The sequencer thing.
Well, especially, but I'm also trying to avoid the shuffle. Like if you can shuffle, it doesn't matter. Well, somewhat it's obviated, but I'm trying in my mind to piece together a place where you did not need to do a shuffle or a global order or something and still maintain some semblance of parallelism that you could inherit from the data source downstream through the computation.
You can do that with sort of thing with Flink, right? So this intentional reason why we're integrating as much as we can with Flink. It's because Flink has the ability to do these sort of updates on subsets of data and then aggregate them later. Right, so if you really do have this case where you have like something's really hot, but you can define in Scala what it means to do pre-aggregation and join the aggregated data, that's very easy to set up as a chain of Flink jobs, and you can feed that off of a Pravega source and type it into a Pravega intermediary and put it into a Pravega output if you want, and go end to end. But it's precisely that flexibility that you have in that Link language that lets you define that would let you get around this.
Well, sure. I see. Yeah, I agree to that point. If there's a shuffle, if there's not a shuffle, and you want to avoid the shuffle, which is a global sync of your whole job and rekey. I mean, that's what I'm trying to mentally play out. If it is possible, if you could somehow use the goodness of dynamic. This mechanism is excellent. If you could somehow use the benefits maximally to not incur a shuffle. I haven't seen anyone do it. I'm interested if it's possible or what it would look like. But if you do the shuffle, then yeah, what you're saying is true, and Flink can handle it, and you can do your pre-aggregates, super aggregates, all that other stuff. But I'm still trying to figure out if there's a good way to do this. Inherit the goodness of the partitioning and the dynamic partitioning, but still not incur this global sync, this shuffle downstream.
Okay, maybe we should keep going and keep the discussion afterwards. This sounds pretty interesting, by the way. Thanks for raising it. So let me mention another mechanism that is important for the way we do things in the Flink connector, which is checkpointing. So the motivation is that if you have an application where frequently or periodically you're saving some local state, and as part of that you flush downstream to make sure that that local state that you saved is consistent across the readers. And then you keep reading, so you're reading data from a Pravega stream. And at some point later, what you want to do is reload that local state. What do you do about the Pravega stream? And so we have implemented checkpoint exactly to solve that problem. And it's useful with Apache Flink. A checkpoint object is an opaque object that maps segments to the corresponding offsets. Right? So we give that to the application when the application requests. So this is an illustration of the process. So if I have that same stream as before with 2 segments and readers, someone through the reader group API requests a checkpoint. In the case of Flink, that will be the master. we have the readers delivering a checkpoint event that indicates to them that they should take any sort of steps that are necessary as part of checkpointing. And once they do that, they coordinate through the state synchronizer, put a checkpoint object together, and deliver that to the request. And in the case you want to reset to that point, you can. So there is an equivalent call in which you give the checkpoint object. So the reader group, so the whole coordination will tell the readers to reinitialize. Once they reinitialize, they can go and resume reading from the positions of the checkpoints. We don't guarantee that the assignment is the same. The assignment can be different compared to what we had at the time of the checkpoint. All right, so let me, before I wrap up, let me tell you a bit about connectors, specifically about the Flink connectors. So the connector has, a connector as we see them has two parts. There's a sync connector that dumps data onto Pravega. So you can have a Flink job that is outputting data and it's going through this part of the connector to dump data to Pravega. And on the other side, we have a Flink job that is reading data from Pravega and processing it. Actually, by the way, the Flink connectors are open source as well. So this is the repository where the Flink connectors live. So the overall idea is that we have sources of data. We ingest that using Pravega, and then that data can be processed by Flink jobs themselves or other consuming applications, or we can even have a pipeline where it goes through Flink and goes to other applications. So we can do any combination based on the data we ingest. So in this picture, I'm illustrating exactly that. So we can have a whole pipeline where we have data coming, being ingested to Pravega, and then going through Flink jobs, go back to Pravega, and then Flink job again, and then Pravega. So we can compose it that way. On the reading side, so one of the things that I had stressed already is that we try to hide that complexity around scaling, and so all the segment of segments is transparent for the source tasks. So any stream scaling, any change of the set of segments is transparent for the source tasks. But one thing that is important here is that when we do a checkpoint, what is the process that we use to actually trigger the whole job checkpoint in Flink? So the master that manages the checkpoint in Flink, it's, when decide it's time, is going to initiate checkpoint. So there is in our connector, if you go to the code, it's going to see this master trigger restore hook, which calls into the reader group, telling the reader group to initiate a checkpoint. The reader group, so the readers are going to coordinate through the state synchronizer, and then they will deliver a checkpoint event. That checkpoint event is going to initiate the checkpoint of the tasks, which is going to start the whole process of taking local checkpoints of local state, issuing barriers, and all that stuff. So once that happens, then the checkpoint object is returned to the master, and the master stores that. Now on the writing side, Flink writing to Pravega, it uses transactions to obtain exactly once. So yeah, I'm sorry that the errors are not showing up really well. So there are errors here between the circuits. And so these are the sync tasks, right? So these are operators, and they so if you're using exactly once mode, they're going to use transaction writes to Pravega. You can opt for not using transactions, just doing regular writes, in which case you obtain at least one semantics. Now, in the way we do this, we're essentially implementing a two-phase commit protocol. The master, which is coordinating the checkpoint, it starts a checkpoint in the way I mentioned, so it initiates a checkpoint in Pravega, and the readers will issue the checkpoint events, which starts the Flink checkpoint steps. They will issue barriers when the sync tasks get the barriers through all the incoming edges. They will acknowledge the Flink master, so the Flink master will declare the checkpoint at that point done. And once that happens, it will notify the sync tasks that it's complete, and then they will go and commit the transaction to Pravega. So this is roughly the flow that we expect to see. And so this is a prepare, act, and commit phase.
Question about the transaction protocol. So you're now doing a distributed transaction, right? It's a just transaction around writes.
Yes, transaction writes on that.
So what if the commit call went through but didn't come back? You will end up writing duplicates next.
So which commit call? So this commit call here?
Yeah.
Yeah, so it's idempotent exactly. So if you try to commit twice, right, the second time it's still gonna stay committed. It's gonna acknowledge. Right? Okay, so I'm ready to wrap up. I want to wrap up by mentioning the core concepts that we have in Pravega. So Pravega is about a number of things, about storing a bottom amount of data on a per stream basis. Storing a stream, as you see it, is about preserving that order of events, so that when you ask questions about your stream data, you can answer questions around that leverage the order in which they have been generated and stored. We want to do all that by making sure that we can provision the capacity of the stream according to the workload that is incoming. We care about providing exactly once on the right path via transactions and duplications, so these are mechanisms that we have implemented. One of the very nice things that we have in the core of Pravega is that we implement a very flexible control and data planes, which enables us to do all that manipulation of segments and implement some cool features as I have shown here. It's designed to be horizontally scalable so that we can accommodate a large number of streams and segments. And reads are also very important because we need to process that data in an efficient manner. So we care about low latency reads as well as reads of distant past data, like historical catch-up batch reads. And there is a lot of ongoing work. I don't mean to say that Pravega is totally done. There are lots of things we're doing. This list is far from being exhaustive. So there are things like around performance tuning, scaling support. As someone asked the question, we give signals to downstream so that whatever is using Pravega data can also scale if it chooses to. Event time support, geo-distribution, security, and a lot more things that leverage all this flexibility that we provide. As we open source project, we're looking to growing a community. So if this is interesting to you, feel free to talk to us, come and interact with us on our repository. And with that, I was going to say that I can take questions. I've already taken a lot of them. So I don't know if you have any further questions. Yeah.
What's the criteria you decide to
split
the seal? Yeah, the seal the segment and create a new segment.
To seal a segment is based on ingestion rate. So you decide on an ingestion rate. And so we do moving averages of the stream during 2-minute cycles. And then, if it goes beyond the level that you have chosen, which is configurable, then we split it.
It's basically policy based. Right now, we just implemented the ingestion rate as the only policy. We can have other policies.
Yeah. That's why I ask.
To deploy this, there's a dependency on Bookkeeper and what else? And a storage backend of your choosing, and what else?
Yes. It's Bookkeeper. There's a dependency on Bookkeeper. So logically, we separate them as tier 1 and tier 2. So tier 1 is again low latency durable writes. And Bookkeeper is doing the job for us today. For tier 2, we have made it a bit more flexible. Well, so both of them are implementable interfaces, but for tier 2 we have more bindings implemented. Right? So we have HDFS, we have NFS, and we have extended S3, which is one of the storage options that we support because it's a product that we offer.
Okay, but there's no cluster manager or distributed key value store or anything else, just Bookkeeper?
For tier 1, you're saying, yes.
Is your question like to run the whole thing?
Yeah.
Do you have some dependency on something else, or do you provide everything to run the thing?
Well, we don't provide the installation today, right? On the open source repository.
So like you have a Terraform here.
Yeah, we have some stuff. We have scripts that I can use to deploy on AWS, and we have container images and all that stuff.
And this example sits on top of EMR. It looks like.
Yeah.
Right. So there are two parts to your question, right? One is the open source Pravega itself.
Yeah.
We have Terraform script that you can deploy on AWS or anything like that, and it uses any HDFS. In AWS case is EMR. That's why we use EMR. But we have a product around it called Nautilus, which actually does the orchestration for you. You submit a Flink query, and it can orchestrate on the available cluster. And while ingestion also, it kind of distributes Pravega segments across, distributes and places them accordingly. And in fact, can place the streaming job, on the right place where the data is streamed into.
Okay.
So that's our product.
Got it. Nautilus. Cool.
All right. Any other question?
Well, you have to ask a question to give away the prize.
To give the what?
We have a one.